I'm going to share this afternoon section. There is a little bit more of optimal transport. So like first, Marco Cuturi is going to talk about computational OT. And later, there is Jan Maas talking about the discrete and quantum optimal transport. So both speakers are in Europe. So both talks are going to be remote. So Marco, thank you very much for the presentation. Are you planning to come here at a certain point in the semester?
Yeah, I was planning to come here, but I was not keeping track enough of the regulations, and I realized too late that I could have applied for an exemption, and so I started bomb emailing the embassy, but I didn't get an answer.
Okay. But thank you. So the floor is yours, Marco.
Okay, thank you very much. So I'm very sorry about not being there with you. I feel a bit like a late night, radio host talking with the audience about some confessions of something. So it's definitely very clearly a very different vibe from the usual one. So it's 11 p.m. here, but I'm very happy to give this presentation today, and I really want to thank the organizers for inviting me. So I also mentioned earlier that you might want to ask questions, of course, and I very much welcome any type of question. This will help me stay awake and make sure I'm not going into some unnecessary directions. So this is going to be a 1-hour presentation, so there's going to be a lot of content. But what I want to stress here is the computational challenges that have arisen from using optimal transport in practice. And by practice, as here, I will be mostly speaking about practice in machine learning and statistics, meaning probability distributions, which are most often high dimensional. This might be like 5, d equals 5, 10, 20, 50, and then a lot of data points. And so those challenges are first to compute optimal transport. And if you look at the title here, I'm talking about differentiable matchings and mappings. And so the idea is not only here to compute transport and to compute this maybe optimal coupling or optimal Morse map, but also to differentiate through this coupling. Meaning if I change the measures or the sampling measures, what happens to the coupling itself? So I'm going to start with an example. I hope Philippe is in the room because this is mostly derived from his work. Yes, okay, he's raising the hand. So he's probably going to recognize this idea. Imagine you have a biopsy, to take some tissue, grab some cells, maybe those are tumor cells or healthy cells, and you want to watch them over time, as they grow. You have this dish and you just try to look at it every 6 hours or so. What is amazing is that the current state of technology in genomics allows us to actually look at the state of one single cell. People call this single cell genomics. And so I'm not going to pretend I'm a biologist. What is basically given to us as machine learning or statisticians is a vector of features that describes the cell at that point in time. So typically that might be the gene expression levels and things like that. One of the challenges, though, is that you can't take a cell, from the plate, take its features, and then put it back, and then see 6 hours later what that cell has become. So what you're basically left with is this situation where you're looking at a bunch of cells, a population of cells at time 0. You're going to sample a few of them. So this is your sample of cells. You're going to put them through this sequencing machine that is going to featureize somewhat each of those cells. And in that process, you're going to kill the cell, of course. And this gives you a picture of the population of cells at time 0, which is a bunch of point cloud, basically. And then what you do typically is you wait 6 hours more. Maybe you add some reactants and things that you want to, include in the system. And then you're going to be, again, left with the option of taking a bunch of cells. Maybe that number is the same or it's going to be bigger. Let's assume for a second it's the same. And so you're going to, again, have this point cloud. But right now it's a point cloud that represents the population a bit later. And so what biologists are confronted with is typically we would like to understand what is the individual trajectory of a cell. If you are a cell that at time 0 had this kind of characteristics, what is typically going to happen to you 6 hours later. But of course, you can't replicate that experiment. And so what you end up doing is the closest natural guess, that I would say, and that's basically going to involve some form of optimal matching. You're going to pretend, well, I had blue cells, like this. Those were my blue cells here. 6 hours later, something happened, nature, continued, and so the cells have grown. I would like to somewhat have a good guess of what this type of cell might have become. And so what you do is just simply look for the optimal matching. And so here, I'm going to be a bit vague. Or if you go back to the previous lecture, I would say it's more like a kind of Morse map that you want to find that would help you tell you, well, basically this cell became this cell became this one, etc., etc. So this is roughly, really at a very basic level, the contribution of the paper that is on the lower left that Philippe contributed to. And I'm saying roughly because there's a lot more to this. Typically, the challenges are that the number of cells maybe is not the same. You have to account for some type of growth in the cell population and other things. But roughly, what optimal transport is going to help you here is to disambiguate this step. It's going to remove the ambiguity of guessing what cell became what cell. And let me just do a bit of plug for some recent effort in my team to package software that is able to do this at scale. We have developed a software called Optimal Transport Tools. And this is one of the, if you're interested in this application, you can of course look at Philippe's paper. And then you can also check our fairly simple implementation of these ideas. So this is just one example, and I'm not going to go into the details of, there's lots more advanced topics in that line. Another area where this idea of computing and matching arises is in fairness. When you want to do classification, that it's going to be a bit mindful, careful about some protected attributes. So typically, let me show you a scenario. You want to predict something out of individual features. So you have some xi's, people, and yi, something that you want to predict. This could be a loan or maybe a health outcome or something like that. And let's keep it simple. Let's assume it's going to be a binary decision. So the idea of using empirical risk minimization is going to be, let's try to find one function, f parameterized by theta, which for every xi is more or less going to match what you have observed. And to do so, typically you would minimize some kind of, basically the average risk. In doing so, what happens is if you're completely focused on minimizing this sum, you might find a parameter theta, which is such that, of course, you will make some errors on some individuals. So maybe the error is going to be distributed across the individuals in the way pictured below. And the error, of course, is going to be maybe bigger and smaller in some individual cases. And then later, what you realize is that you are doing more systematically errors in subpopulation. Let's say this is the greens compared to the purples on the left. And to highlight this, I've just plotted, for instance, the histogram of errors in the left population and in the right population. So here again, one of the ideas that has emerged recently is to enforce some kind of fairness mechanism that would be operating on this level, basically at the level of the distributions themselves. So you would say, for instance, a fair classification for a loan would be such that, for instance, the distribution of errors done on the purple population is more or less similar to the distribution of errors done on the green population. And in the same time, this might be, for instance, you could even say, I'm going to enforce like the median error is the same on the purple and on the green. And there's other works, and there's really a lot of works recently that have looked at this idea of using optimal transport for fairness. Other people, for instance, insist on saying that a fair treatment would be one where a median person, whatever that means, in the green group is more or less treated equally to the median person in the purple group. And so again, you will need to do this type of matching, either in one dimension for simply to match the errors, or of a population against the other to say that, okay, maybe if you're a university and you want to hire students from a country A and country B, then a fair treatment might be to say that you're treating equally, the median student in country A that you're treating the median student in country B, and therefore you need to have this kind of matching. There's lots of okay, this is one example that we've covered in the toolbox. There are lots of examples like this where matching, the intermediate step of matching appears naturally as a way to help you basically learn something more complicated. I have other examples in neuroscience where, for instance, you would do some form of registration of the data when you have different brain activation maps. Everybody has a different brain, and when we have some stimulus, we might have a different area of the cortex which is activated, but still we want to be able to do this matching to say that to have something that is comparable. And let me just also illustrate an example that comes from domain adaptation, machine learning. A typical problem where you have data which is labeled, you have red and blue points, and then you have a bunch of not labeled data sets. This is something that you will probably try your classifier on later on, but you don't have labeled data for it. And so one idea that has been in the air in the last 4 or 5 years or so is basically try to do some kind of matching between what you have in the train, which is labeled, and what you will have in this other data set. This involves doing some kind of optimal transport. Then you are going to transport the labels and then learn some kind of classifier. So this is a bit a mix of problems where essentially an intermediate matching or mapping, or I could almost say coupling, since you're familiar already with the vocabulary of optimal transport, is going to be needed to help you disambiguate. There is a strong prior that exists on what such a matching or mapping or coupling might look like. And that prior is typically going to be what I would expect to be a matching should have a low cost. So this is the main ingredient in deciding, when you have a ground cost, what is the optimal matching to solve the optimal transport problem. And what I think is interesting in the machine learning perspective on optimal transport is that it is rarely the case that this matching or coupling or mapping is really the end goal. I would say that in the earlier literature on optimal transport and applications to data sciences, maybe doing that matching was enough. This was sufficient maybe for a given task. I would say that in the recent years, the focus is no longer really on computing the coupling itself, but rather parameterizing that optimal coupling as a function of the cost parameters or some representations of the data that you can tune in order to basically minimize some kind of loss after that. So it's going to be important not only to compute optimal transport, it's also going to be important to differentiate through it. And so if you look at this, I haven't used too many keywords from the optimal transport literature. The biology example actually I think can be understood by anyone without any background in optimal transport. And so when you start digging into what you need to actually provide this set of tools, well, you realize that it's great to have a toolbox that is guided by theory, that is robust and versatile to accommodate different types of data sets. It will need to be scalable. So this is a typical challenge that we've been facing in the last 5 or 10 years. And the differentiability is, I would say, a more recent addition, maybe in the 2 or last 3 years. And that toolbox, that theory, is basically optimal transport. And so what I find remarkable in the field is that many of the challenges that I've been enumerating were covered in mathematics with a lag, of 5 or 10 years ahead. So differentiability, for instance, is a clear one. But every time you want to actually adapt it and make it work, on real data, there's a whole new sort of challenges that arise at the same time. So it's one of those fascinating fields, I feel, where there's a confluence of interests. And so just to illustrate this, maybe it's well known that this field is super important in economics. And historically, this was the development of this theory. And it has spanned a lot of attention, it's spanned a lot of developments in applied math, pure math. And again, a small plug for a recent work with my colleague Gabriel Perret. We've been focusing more on the numerical issues in the last years with this book, which is a bit of a survey. But I have to say that this survey is now almost 2 years old now, so it feels a bit outdated in some respects. So we will probably need to refresh it pretty soon. I think you've had this wonderful introduction this morning to optimal transport. So I will start directly, basically from where you left. You ended the course, and this is basically the definitions of the various definitions of optimal transport. So it's already a bit complicated because, as you can see, depending on your interest, you might have various definitions of what constitutes optimal transport. So the two classical ones, I would say, are the Morse formulation and the Controvic Primal formulation. So this inf of a t that pushes forward mu to nu of this integral of the cost of the displacement. The other one, of course, is the Controvic dual potential. So I think I have more or less the same notations that Michaela's slides, except that here I think she was using a gamma here, whereas here I will be using a p. And I don't know what the dual formulation was, what the notation was for her dual problem. This, I will use those notations in the continuous setting. Is there any question at this point?
It was the same. She used minus b and minus c. So.
Okay. So in here, you mean?
For the dual, yeah.
For the dual, okay. Yeah. I guess this is, yeah. This was it for the squared Euclidean distance cost or for the general cost?
For general cost.
Okay. Yes, sometimes you will see an f minus, a phi minus psi and things like that. Here I would just be using a plus. Apart from that, everything sounds okay?
Yes.
Okay, great. So as I said, the lecture is going to be short, so I have to speed up a bit already. I'm going to focus on what matters too, and here I have to write maybe ML stats, practitioners. Okay, it's not going to be a lecture on, let's say, applying, looking at optimal transport from the perspective of gases in 3D or fluids, or let's say reflectors to design, the lights of your car. There are lots of applications in optimal transport that are fairly low dimensional, where what I'm going to say right now does not apply necessarily. I mean, you can argue, but as soon as you start, dealing with data sets which are large and in higher dimensions than 2 or 3, then I would argue that what a typical practitioner of optimal transport or machine learning and statistics would want to is to have the following setup. We have samples, x1 and xn, y1 and ym, let's say. So here I'm just on purpose using a small, different quantity here. And so I'm going to I will have to deal with empirical measures, so a bunch of data. And what I want to do is typically compute this quantity, these 3 quantities, on actual empirical measures. And this means either focusing on the quantity itself, or also maybe focusing on the T star, the P star here, and the phi star, psi star. Okay. So I want to compute either the optimal transport cost or the solutions in either of those 3 settings. And so in that scenario, what a practitioner would clearly ask is, how expensive is it to compute this quantity that you just gave me earlier in the slide? And maybe if you are interested in deep learning and end-to-end learning models, as is now really dominant, how can you differentiate from this? And if you're a statistician, or even just a practitioner for that matter, you might also have, like the second order question would be, how meaningful would be that computation compared to having access to the entire distribution? If I had access to the entire mu nu, does it actually make any sense to work hard to compute the distance or the solutions to this optimal transfer problem between samples? Can I compare it with what I would know in theory if I had access to entire distributions? So those are two questions I think that are important. And whenever you will need to sell optimal transport to a different community, this is clearly the two things that people will ask. So again, ML stats, I will assume that I have access to points. So in the first setting, in the Morse problem, well, this arises when you want to compare, for instance, the 2-point clouds that I told you earlier in biology. So you have, let's say, 100 points, that describe 100 cells, and then later, because this is going to be a Morse map, so we're going to assign one to the other, we're going to assume there is 100 points on the right-hand side. Was there a question? No, I guess. So in that case, if you just plug really the definition, so it can either be this definition or this definition. If you plug either of the two definitions, you have something which is simplified to the optimal assignment problem, which is simply a question of finding an optimal permutation. And it's simply going to be finding an optimal way that is going to assign 1 point of the red measure to 1 point of the blue measure. And we have decent algorithms for this. One of the most famous algorithms for this problem is called the Hungarian algorithm, which was discovered in the early 20th century and then represented later in the 50s. And what we essentially know is that this is roughly cubic when you implement it. And there are cases where this could be brought down, the complexity can be brought down a bit further if you start assuming things on the cost structure, for instance. So already you can see that, I mean, the cubic, exponent is starting to pop up. And what typically we would want to do in a more general setting, not only covering the Morse problem, but rather covering the Controvic problem of finding a coupling, is essentially solving this Controvic problem, the inf of the couplings, blah, 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 for those two measures. And so if you, again, directly plug this definition here with the data that I just provided here, this is the mu, this is the nu, then what you have, you just need to write it down, is the following problem. It's going to be comparing the two measures and somewhat isolating what I would call the geometry of the problem. The one thing that only focuses on the cost between 1 point xi and 1 point yj. So this is basically going to be your cost information. From every red point, you're going to look at every blue point, and this is going to give you an n times n matrix. And then the other thing is just the constraints of the mass conservation constraints, which are such that you essentially want to have a look at all matrices of size n times m, okay, such that the row sums coincide with the weights that you are given a1, an, and the column sums of this matrix P must coincide with the weights B1, Bm that you were given. Okay, so we have two measures: weights A, weights B, locations X, location Y's. We split X and Y. We take A and B, the weights apart. X and Y help us define the cost matrix. A and B help us define the feasible set of matrices. And then we are essentially going to just run a linear program on this. We are just going to look at the matrix P that satisfies this mass conservation constraint with the smallest dot product with the matrix of distances or costs. So far, so good? Okay, so let me just, before we dive a bit more into this problem, say that, of course, remember a few slides ago, I mentioned this dual problem, the Controvic dual problem, which is about potentials, optimizing two potentials such that the integral of each potential against each measure is maximized with the constraint here. I didn't really write this very clearly, but this means basically that phi of x plus psi of y is going to be smaller than c of x and y. Okay. Oops, sorry. Yes. So this is the constraint. So if you again simply just reinstantiate this dual problem on the two measures that I gave you here, like this, then what you just have is this dual problem, which is going to maximize. So this is playing the role. You could almost write it as a phi vector. This is going to be a psi vector, okay? And you're going to integrate against the measure, so you're just going to sum up values, the values of alpha and the values of beta, and then you have this dual constraint on the cost. And what is, I think, important to have an idea of is that essentially the reason why we have the dual problem is because we want to have guidance on what is basically causing this optimal transport to be expensive or not. And this is going to play a role later in when we're going to try to differentiate. So let me try to give a more concrete explanation. So here I'm going to, let's say, solve the optimal transport problem, the primal one, the one that we're used to, between two measures. This is the blue and the red as usual. And this is going to be a matrix of size. So here we have 1, 2, 3, 4, 5, 6. So n is equal to 6. Here we have 1, 2, 3, 4 targets. So m is equal to 4. So the matrix, the optimal transport matrix is going to be this 6 times 4 matrix like this. It's going to have a few non-zero values, okay? And the non-zero values are exactly here pictured as lines that connect one red to one blue. So this is what you get when you solve the optimal transport problem in the primal form. You have basically this idea of transfers of masses between inputs and targets. What we have, if you solve the dual problem, of course, it's something completely different. It's no longer an idea of interactions between the inputs and the targets. It's just simply a set of values which is indexed by each of the points in your measures. So for each of the 6 red points, we have 6 values, and for each of the 4 red blue points, we have 4 values. And let me just plot you actually the actual output of this optimal dual problem. So what you have here is essentially those 6 values. So I've plotted the values at their points, at the locations, and to plot those values, I'm using a color coding, basically. And here, I'm doing the same thing for the blue, the 4 blue points. Okay, so I'm going to remove this. So what you can notice here is the following. So first, there is an invariance with respect to a constant factor, meaning if I raise all of the values of the alpha, the dual variable for the first measure, by a constant and decrease it by the same constant to the blue measure, I will have the same objective, and I will also satisfy the constraint. So therefore, there is an invariance to an additive constant. So you should look at these values here relative to each other, not really as an absolute in absolute terms. What you can see on the right-hand side is that those red values here are, the values here for the red points are essentially starting at the lower bottom, minus 40-ish, and then go up to, let's say, 0 here. So the largest dual variable is this value here for the input measure. And for the target measure, the blue, of course, it's here just in convention because in the Controvic problem, everything is symmetric. But the target blue measure, the highest value is reached basically here on those points here, because this corresponds to the whites of the color map. And essentially, the lower ones are reached here in the middle. So what you can see is a pattern where, relative to each other, the highest values for the input measure are found here, and the highest values for the Tucker measure are found here. And what this is actually telling you is some form of sensitivity analysis, and this is well understood in linear programming. This is basically telling you there is a price to pay for each unit of mass, which is right now available in each of the points that I'm plotting here. And that price to pay, if you were to simulate some kind of mechanism to fix the price of the optimal transport cost between the blue and the red measure, would be those values. And what you can very clearly see is that the largest values are happening in those points which are a bit further away in the transport. So intuitively, on the left-hand side, you can see that this is actually going to be a bit painful in terms of transporting things from red to blue. But what this is really quantified in the dual problem here on the right-hand side. So imagine, for instance, the red distribution is a distribution of, let's say, bakeries, and blue distribution is a distribution of stores or like restaurants that need the bread. If you were a planner and you wanted to change the distribution of either bakeries or restaurants to minimize the transportation cost, well, this is typically where you should be looking at. You should be looking at this drawing to say, well, it seems that if I had to decrease the production of one bakery, it should probably be this one. And if I have to decrease, for instance, the amount of bread that is needed from restaurants, it would probably be the one on the lower left. On the other hand, if I want to change the locations of the bakeries and the restaurants, I should probably look at this thing here, because this is going to tell me basically that maybe this bakery needs to move a bit further, closer to this restaurant it's serving currently, and vice versa. Okay, so this was a bit of intuition, on the Primal and dual problems and what they provide you in terms of sensitivity. Now, so far I've mentioned, this is a linear program. It's easy. We can solve it. So the truth is that it is indeed relatively easy. So if you look at this from a geometric perspective, here you are, let's say, in the space of matrices of size Rn times m. And among those matrices, you have a convex polytope of matrices that satisfy the marginal constraint. And you have one vector, which is summarizing, again, the geometry of your problem. And this tells you everything about, the transportation cost. And of course, the goal here is to find the coupling that is going to minimize the cost, the dot product. And this is going to be here, this P star in this example. So if you just want to address this problem in full generality, you make no assumptions, for instance, on the cost, which is actually important in many machine learning applications. Then the default approach to handle this would be to run a network flow simplex solver, which is a specialized form of linear program for network flows. And this is typically a supercubic complexity, worst case complexity, and you can also observe empirically that this grows cubically. And so on the one hand, remember that this P star already has size n times m. So what this tells you is that you have a variable set which is size nm. You would need nm square, let's say a cube of that, from square to cube to optimize. So that's already quite satisfactory. Similarly, even if you're solving the dual problem only has n plus m variables, but the constraint set is already also nm. Remember that the dual also has a size of a constraint which is quadratic. So all in all, it seems to be a fairly reasonable thing to hope. But this is still a bit problematic in many machine learning applications. It's very difficult to convince a practitioner that you have to go cubic in terms of computations to introduce a new tool. So this is more or less doomed to fail already. And this is why this Earth movers distance, as people called it in about 20 years ago, when he introduced first optimal transport ideas in machine learning. Well, there was a bit of a fashion, and then after a few years, it faded out because the cost was just too big to bear. Let me just say another thing, which, again, another bad news in terms of computations, I believe, which is that if you look at this linear program, of course, linear programs have been around for like 70 years now. So we understand them very well. And it makes sense, you know, to compute the value of the optimal value. What we know, though, is that the solution of optimal transport or of network flow problems or linear programs is extremely unstable and not always unique. And so if I just go back to the initial, you know, motivation of my talk, remember in biology, what people want to do is not just, you know, find an optimal matching per se to minimize the cost. They are interested in the argmin itself. They're not interested just in the minimum value, which is the output of this linear program. They're interested in the argmin. And if you look at the argmin, well, imagine a little bit what this is very classic, you know, linear programming sensitivity analysis. But imagine a little bit what would happen if you were to perturb a little bit the inputs. So here I'm going to perturb. This is the primal problem. I'm going to perturb x, you know, the locations of, let's say, the bakeries. If I just perturb things, it's a bit as if I was, you know, changing a little bit this vector here. And so for a while, what you can very clearly see is that the solution, even if you perturb a little bit the inputs, is not going to change until the moment, which never happens in real life, where the cost is going to be orthogonal to a facet of the polytope. And then all of a sudden, what will happen in real life is you will jump, you know, from a P star to another P star. So if you go back to the biology, you know, the matching problem, it's very intuitive to see that, you know, if you're looking at two different point clouds and you perturb a little bit the point cloud, then for a while, you know, the optimal matching will stay the same. And then all of a sudden, maybe a really infinitesimal move will trigger a switch, you know, between the matchings. So what this means essentially is the Jacobian of P star with respect to, let's say, dx is either 0 or infinity. Okay, and since most of machine learning today is based on some form of gradient or first order differentiation, you can immediately see a problem if you will need to focus, you know, to use this P star in your machine learning pipeline. So first, this means that the objective itself, the minimum, is not differentiable everywhere. So there are basically some breaks. But what is, I think, more problematic is that the argmin itself is technically differentiable almost everywhere, but its derivative is 0 almost everywhere. So this is this is a list of, you know, negative aspects of using the plugin estimator of optimal transport in machine learning. And let me just add yet another one, which is that the complexity of those algorithms is actually pretty heavy. Not complexity in terms of computational complexity, but actually implementing them, running them on parallel architectures. It's very difficult to scale them properly. I think everything is kind of, you know, working hand in hand. If it's hard to implement in matrix or linear algebra, it's hard to differentiate, and it's hard to run on GPUs or parallel hardware. So everything is more or less tied. So the other important criticism that people would make towards, you know, plug-in estimation of optimal transport, and here again, this would deserve an entire lecture on its own, is basically the idea that optimal transport has to deal with the curse of dimensionality. If you have dimensions, if you're studying distributions which are in dimensions 5 or 10, you will already start hitting this problem, which is that to have a good estimation of the optimal transport between two densities using samples, you will need an exponential number, a number of samples that is exponential in dimension to have a good quality of the approximation. So let me just very briefly mention this, because there's a whole body of work on this, and I'm not the most qualified person to discuss it, but this has been driving a lot of, you know, research interest in statistics. I know Philippe has been working on ideas related to this, or on trying to, for instance, find bounds on recovering the Morse map. But other people have been working also on trying to, you know, add some conditions on, or a hypothesis on the smoothness of the densities to get better rates. But anyway, my main message here is the picture is a bit bleak if you just stick, you know, to the gospel, I would say, of Morse and Controvic. So what I want to basically motivate here is that if you are interested in optimal transport and you want to be a bit opportunistic and think that you want to apply this to real life problems, what you're going to have to deal with is those two aspects. Computationally, it's fairly heavy if you really take the Controvic definition. I haven't really talked about the Morse definition because usually it's a bit less relevant in stats. The Jacobians are 0 or infinite if you look at the arguments, and this is one of the reasons why people use optimal transport, this idea of matchings. And statistically, it's a nightmare. Everybody knows that this is really not a good place to be to estimate this quantity. So my main message here is that if you want to use these ideas in data science, you somewhat have to adapt them. You need to add some kind of learning perspective on this. You have to impose some kind of prior inductive bias, people call this. And so somewhat you just need to regularize the optimal transport problem to improve on either or preferably both aspects. And so again, since there's at least 3 canonical formulations for optimal transport, the dual Controvic, the primal Controvic, and the Morse, you can see there's lots of opportunities here for creativity and to start, changing, tweaking things to introduce some prior. So one of the obvious things is when you start running, the dual Controvic problem, and you want to run this on functions, you will restrict your space of potentials to something which is has some properties. So this could be an RKHS of functions. And so this has been used for a few years now. There's a very interesting recent work by a former colleague, student of mine, and Francis Bach and Alessandro Rudi and François-Xavier Viala, a lot of people, that was published at COLT this year. The other important thing to know, I guess you talked a bit, maybe I didn't look into the details about C convexity in the previous lectures, but what you might know is that if you instantiate the optimal transport problem when the cost is a distance, then the dual formulation has a simpler form. It is very nice. It is basically the supermem of our Lipschitz functions. It's like an integral probability metric, so it's supermem of Lipschitz functions of the test or the integral of the function on the differences of the two densities. So in that case, there has been a big boom, in machine learning by optimal transport thanks to this Wasserstein-Gein paper, who basically introduced the idea of parameterizing those one Lipschitz functions as neural networks with rectified linear units and constraints on the weights. So this was a fancy way to parameterize one Lipschitz functions and then run, standard stochastic gradient ascent to optimize this. There are some other results that apply, but in lower dimensions, you see wavelet decompositions. Then let me just also mention some nice recent works that use a specific class of neural networks that are convex with respect to their input. So they are called input convex neural networks. So you might wonder why input convex? Well, it's because they're convex with respect to the x and not with respect to parameters theta that form them. So this is just a naming thing. So if you compute the Wasserstein distance, so the optimal transport problem between two measures, when the cost is the squared Euclidean distance, okay. Then you can also parameterize the dual problem as a supermem of a class of convex functions, where you're going to introduce the Legendre conjugate of the function f. And so in that case, what people have been doing is introduce a class of neural networks for this family of functions f, and then they do tricks to more or less approximate the f star. So this is recent work. You can also try to regularize the primal optimal transport problem. Again, I want to stress that everything is for grabs in the sense that you just take the original definitions and just try to adjust, to change things so that they suit better your application. So people, of course, have started thinking about changing the cost somewhat, making it simpler. So one immediate way of doing it is thresholding it, or assuming that the cost is the shortest distance, shortest path distance on a graph, or things like that. This simplifies the computations a lot, even in the LP case. The other thing you could think about is, if you're giving me two measures, I'm going to project them on a set of densities or measures. So typically this could be approximating a measure by a Gaussian and then using closed form formulas for Gaussians. This could be using k-means if you have a lot of points, and then compare the two k-means distributions, do quantized distributions, rather than comparing the two distributions directly. There's also a trend which is to project the measures first on a smaller subspace and then compute optimal transfer in that smaller subspace. There's lots of ideas, and there's one that I'm going to talk a bit more in particular in the last minutes or so, which is about entropic regularization. And so the idea, let me just very briefly mention the idea that you can also try to regularize the Morse problem, and this essentially is also using the Bronier Theorem, which tells you that for the Morse problem, when the cost is squared Euclidean distance, you know that the optimal transport is the gradient of the convex potential, of the convex function, sorry. And therefore, you can try to find the convex input convex neural network whose gradient, when you push it forward to mu, makes it look as close as possible as you can. And so if you, depending on what you mean by close, you will have different types of algorithms. So recently, we've been exploring the idea of actually using a form of sample-based delta for the Wasserstein distance between those two measures. People have also used the Kullback-Leibler divergence and placed themselves in the framework of continuous normalizing flows. There's a lot of ideas out there, but I'm sorry, this is a bit of an accelerated, mention of all this. Let me just focus on one which I've been working a lot on in recent years. So the motivation for entropic regularization essentially goes back to this geometric picture of trying to solve this linear program. And the wish list for this is to have something that is more scalable, that is more stable, and differentiable automatically. Maybe I will explain later what I mean by automatically, but differentiable with respect to the inputs, such that in the sense that if I'm able to find something that is here that I would call my P star somewhat, maybe not the optimal one, but something of a slightly different definition, but that this P star is easier to compute. This P star, so let me just put a gamma in front of it so that I explain that this is a different notion of P star. I would want basically this thing to be differentiable with respect to whatever I want. And I would want this P star gamma to be relatively cheap to compute. And the way to get there is essentially to introduce regularization in the linear program. And here, I will introduce this in the primal setting. In the primal setting, you have this linear objective, linear constraints. You just have this gamma times entropy of P. This is an idea that dates back to the 60s in economics. And if you just add this gamma times entropy, you are essentially adding a gamma strongly convex regularizer, gamma entropy, a gamma strongly convex regularizer on this polytope. And by here, what I mean by entropy is just the classic Shannon entropy. And what you observe is that if you add this regularizer, the spirit of this regularizer essentially is to go further away from the Morse problem, still more. So somewhat there is a hierarchy where the Morse problem, remember, maps one point to another. The Controvic problem introduces couplings to allow you to map one point to many, but usually in practice, you might map only one point to a few if you're in the discrete setting. What we want to do here, so this is what would happen with the gamma is equal to 0, so no regularization. So you have Controvic or Morse, which really look alike in this setup. When you increase gamma, essentially you want to have more entropy. And what it means to have more entropy is to have more blur. And the blur, you want it to be in areas, typically, because this is regularizer, where you don't want to trade off too much cost. So you will start seeing blurs appearing in areas where you're not really impacting too much the cost. And when gamma goes to infinity, essentially you're left with the coupling which has maximal entropy, and that's just the product of the two marginals. Let me now focus a bit on the computational side of this. Why is that an approach that is popular? It's essentially because if you just write the first order conditions for this problem, so I'm going to be a bit fast here, please, I apologize for this, but if you just write the first order conditions for this problem, so this regularized linear program, what you realize is that the optimal transport matrix, this P star gamma, P gamma here, has a very specific form. It is factorized as a diagonal matrix times a matrix K and then another diagonal matrix. So this makes it, makes this coupling very specific in the sense that it needs to be factorized as two diagonal matrices, left, right, and then in the middle of this matrix K. And this matrix K actually is given to you. It's just simply the exponential of minus the cost matrix that I represented earlier. So this is just first order conditions, just a very simple consequence of elementary principles. But what this provides you is a factorization for the matrix, which then you can also exploit the fact that this matrix is in the set of constraints, that we are given of the row sums and column sums. And this yields a very simple algorithm, which is called the synchronous algorithm. So essentially the regularized optimal transport problem here consists in finding the U and the V such that this matrix here satisfies the marginal constraints, A and B. So if you just work it out using really elementary calculus, you realize that you want this matrix to have row sums A and column sums B. So you're taking the transpose here. And so if you just do a few steps, of elementary computations, what you end up finding out is that you need to have a U and a V, which satisfies this fixed point equation. You want U that is equal to A divided by K U, V, sorry, and V which is equal to V, B divided by K transpose U. This algorithm is actually very easy and very trivial to implement, and people have been studying it for decades now, and there's been a bit of a surge of interest in this algorithm in recent years because of its applicability to optimal transport problems, and so we understand quite well its convergence right now. And in many cases, we can actually make the most of it, to make it scale to large sizes of points. So let me just make a brief parenthesis here to mention that here I just derived this synchronous algorithm by focusing on the primal optimal transport problem, regularized primal. This is a convex problem, so it has a dual. The dual is simply this thing here. And it's interesting to compare the dual of this regularized problem with the dual of the original optimal transport problem. Essentially what happened is that the constraints that we had here, remember in the dual problem, the constraint that told you that alpha I plus beta ij had to be smaller than the cost xi yj, have disappeared, and they became a big regularizer here. And again, I don't want to just to demystify a bit this synchronous algorithm. It's essentially just block coordinate descent on this dual problem here. So let me just skip a little bit. I have a few slides to explain the interaction between this quantity that you can define using the regularized optimal transport problem, like my P star, compared to using the true P star, and coupling, which would be the maximally entropic coupling. But I'm going to skip this because I want to reach the end, which is now I'm going to focus in the last minutes on the differentiability of the Wasserstein indices, or the optimal transport, this optimal transport criterion, and later on the optimal matching itself. So let me just explain a bit what I mean by differentiability here, because this could be several meanings. One of the first things that you can think is what happens, when you have these two distributions, when I'm going to modify the weights of the first measure. So this is one source of differentiability that you want to understand. So by this, I mean, imagine I change a little bit, the weights. Typically, the perturbation would sum to 0, so that the weight vector A is still equal, sums to 1. So what I want to know is basically, how will this Wasserstein distance vary as a function of this delta A, right? And if the other way you can vary basically the optimal transport problem, of course, is by changing the locations. So by this, I mean adding a delta X here, which is going to switch a little bit the locations. So what I want to really insist here is that if the only thing you want to find out is how the Wasserstein distance or the optimal transport criterion itself will change with respect to changes in the weights or the locations, essentially this is always going to be a result of the Danskin's theorem, which tells you that you're basically, let's say, writing something which is going to be f of a is equal to a minimum of g of a and x, okay? And x is in a set. And then this is more or less going to be equal to g of a comma x star, if x star is the argument. And so how f is going to vary with respect to a is more or less how this function would vary with respect to a. You more or less freeze, the optimal solution and then pretend things change that way. So if you do that, either with the weights or the locations, everything is easy. So I have slides here to explain this in more detail, especially with when the cost is square Euclidean distance. But if you just think about what I just told you, you just run dual optimal transfer problem or the primal optimal transfer problem. You solve P star or the dual potential star, and you freeze them, and then you just differentiate the objective function of the optimal transfer problem. This is a different story now if you want to differentiate with respect to P star. So here, for instance, again, what I want to illustrate is that this differentiability is basically going to focus on the difference between the objectives, okay? So computing this difference between the objectives is going to be easy. So here by this square, I'm basically meaning any input variable of interest. So this could be the measures themselves, some parameter which parameterizes a representation of your points, parameter for the distance, a parameter for whatever. Basically, you will always be able to fall back on your feet. What is going to be more difficult is differentiating this P star. And as I said earlier, here in this case, maybe here this is so difficult that it's trivial. This is just going to be 0. But if you want to be able to differentiate this P star, you will need to go a bit deeper into math. So there's 2 ways you can actually do this in a meaningful way. The first one is if you look at the regularized perspective that I just mentioned, is to look at this from a programmer's perspective. So what does a programmer see when I describe the Singleton algorithm? So the Singleton algorithm is just a sequence of operations which starts from a simple initialization, go through a loop of updates, and then in the end return whatever estimate I had of the optimal transform matrix at that moment. If you program this, if you're able to program it in elementary steps like this, then you are able to differentiate it automatically with any of the automatic differentiation frameworks such as PyTorch, JAX, or TensorFlow, etc. So I would say this, if you want an even more crude, example of this, you could almost think of this as a neural network that you have parameterized completely in terms of what each layer is doing. You just give it data. The data feeds, creates a data matrix, distance matrix. Distance matrix is turned into a kernel matrix, and then you just run, the Singleton loops, which are element-wise matrix vector products and element-wise operations, and then this outputs a matrix. So this was actually leveraged in several papers in recent years, and it actually works quite well. But there are some documented issues with automatic differentiation, one of them being that this can have a very large memory footprint. The other one that I would like to bring forward is more, I would call it a mathematician view. And to describe that, I'm going to use this regularized optimal transport problem in the dual. So remember, I introduced regularized optimal transport as, a minimum of P, comma C minus gamma entropy of P. And I told you this is the primal, and the dual is this thing, which is basically this thing here. Well, I'm using the dual because it's simpler, because it's an unconstrained optimal, it's an unconstrained convex optimization problem, maximization problem. So basically gradient descent or gradient ascent here should work at some point. And first order conditions are trivial to characterize. So this is the energy that my optimal transport problem in the dual is going to optimize. And here I've been careful to keep track of everything that is included somewhere in my computation in the energy. What I know, and what the Singleton algorithm is going to do, is essentially cancel those two gradients, one after the other. The gradients with respect to alpha and the gradient with respect to beta, which I have here in closed form. Now, I'm going to just simply introduce something, which is a vector valued function h, which will take all of those inputs, and it's going to just produce the values of those two gradients. And what I know is that this function h, if I have to evaluate it at the alpha star and beta star, this should be 0. I'm just saying here that the gradient of a convex optimization problem at the optimal solution is 0. So to sum up, I can imagine my optimal transport routine is a mapping that takes inputs, measures, cost, regularization parameter, whatever, and outputs dual optimization variable. As we saw earlier.
Yes, I am.
Sorry?
Hey, I'm doing well. How are you?
Sorry, I'm sorry, I hear a voice. Okay. So this mapping is basically taking whatever you gave, this optimal transport routine, and now putting the solution. Here I'm focusing on the dual variables. What I know, if I store, the gradient, so this is the gradients of the energy with respect to alpha and with respect to beta, which turn out to be, and this is quite nice, the marginals of the matrix that you get at that moment for the alpha and beta. But let me just please ignore this for a second. What I know is that if I inject the optimal solutions to this h function, then I should have 0, because this just simply means that I've reached the optimum. So what I have is basically a root of this h function. And our goal is to compute variations of f, variations of the optimal transport solutions, with respect to any of the inputs. And the way to do this, canonical, of course, is to use the implicit function theorem. So the implicit function theorem is just going to tell you that this output varies as a Jacobian as any input. Here I'm calling this a black square. In the following way, this is the formula. It's going to be the Jacobian of this root function here, first order conditions function, with respect to whatever input variable you're computing, evaluated at that variable in alpha star, beta star. And then you will need to do an inverse, which is going to be on the Jacobian this time with respect to the optimization variables. So this is what you have. Let me just conclude to say that in machine learning, typically, we are not interested in just computing the Jacobians of something per se. We're interested in computing the gradient of a loss, which might depend on this R minimum. So if you go back to the biology example, essentially, we have a loss function that will depend at some point on the optimal mapping or matching that we carried out. And we want to be able to compute the gradient of that loss with respect to some parameters. Then if you know about this, the reverse mode of differentiation, then you know that what really matters is not so much instantiating this huge Jacobian, because that would be a waste of memory and time. What you really need to do, and the only thing you want to do, is to be able to apply the transpose of this Jacobian to any vector. And so this is basically what you would do if you don't want to go this automatic differentiation route. People call this unrolling also. If you want to do implicit differentiation, basically you just start from this implicit function theorem that tells you that this is Jacobian. You transpose it and you apply it to vector z. And then you're wondering, this is a huge and horrible formula. Is there any way someone can take care of this for me? Because in theory, this should be actually already known to the program. Well, there is. This Jacobian here, and its transpose, you can instantiate it using typically routines, like JAX, JVP, Jacobian vector product. The linear solve system is going to be handled with typically conjugate gradient here because the matrix is positive definite. And then this latest application of yet another Jacobian transpose is typically handled with the JAX VGP as well. So I'm running a bit over time. I started a few minutes late, so I'm going to end many minutes late, sorry. Just to say, so the message here is if you want to differentiate through this optimal transport and you are interested in this implicit differentiation, but you don't want to know too much about it, you don't want to know too much about the details themselves, then you could try this toolbox that we've been developing, because it's precisely the type of numerical challenges that we've been covering in that toolbox. And so just to illustrate this, you can very easily compute, for instance, the Hessian of the optimal transport distance between 2 point clouds with respect to weights. This is automatically computed for you without you having to write anything. So this concludes my talk. I'm sorry for being a few minutes over time. My main message is, optimal transport theory is there. If we want to apply it to data, we need to regularize in a way or another. And I believe that this regularization should not only cover the idea of computing the distance itself or the optimal transport, but also be able to be differentiable friendly. And here I presented two canonical ways of doing so. For the case of the entropic regularization, I think there are other types of regularizations where you could try to do that as well. Thank you.
So thank you very much, Marco, for this very nice talk. Is there any questions?
Yeah. Can you give a concrete example of differentiating through the why you would want to differentiate through, say, P star or the?
Yeah. So this is a very good question. So typically one I mean I would say this is a bit the bleeding edge of work in applying optimal transport in algorithms. So one of the very classical problems, and again that I provided earlier, is this idea of optimal matching. At some point, your algorithm is going to take as an input some data. It's going to match it to some references that are important to you. And this matching is maybe parameterized by something. Typically, that may be parameterized by a representation of your data or a cost, a matching cost. And then from there, you will use this representation next to, let's say, define a classification rule or something like that. So it's very common, for instance, in, let's say, images, patches, you will need to do some kind of matching between some patches and some concepts that you have. One idea that we've been exploring in the last years or so is also the idea of sorting, differentiable sorting or ranking. The idea that ranking, values, real values, is the same thing as doing an optimal matching between values on the real line and integers. And so there also we need to have some form of differentiability of this ranking step. So I would almost even claim that all of the works that have been using optimal transport so far have been doing this by assuming that the cost structure is known. So typically, for instance, in your work in biology, you would project the data to PCA dimension 30, and then from there run optimal transport and start that the cost is given. If you were to think about, is there a mechanism that would help me learn the cost structure such that maybe some end metric, some end result, some end error is improved, then you will need to differentiate through this matching.
other questions?
Yes, the second question.
Oh, yes, please.
You mentioned earlier that the optimal transport computation suffers from curse of dimensionality. And that's why people usually like regularize, and you introduce like several regularizations. I'm just wondering, like with the regularization, how much gain do you get from this like statistical guarantee?
So there's lots of work. So typically, if you use entropic regularization, you know that you fall back on some kind of 1 over square root n type of bound, as opposed to this exponential number of samples. But I would say that everything is a bit tied in. If you have statistical instability due to this curse of dimensionality, you typically will recover it when you're going to optimize through optimal transport, because you will have very unstable matchings that will guide your learning process. And so you also observe this, when you start regularizing, that it somewhat stabilizes the learning process. So one of the problems with regularization, however, is that you start introducing a bit apples and oranges. So if you start looking at, for instance, the sample complexity of regularized optimal transport with entropic regularization, that you're not looking anymore at the true optimal transport. And so I think this induces a lot of different viewpoints on the same problem. So I don't think there's an easy answer to your question.
Okay. Yeah, so it's probably a naive question, reflecting my lack of knowledge of the need for differentiability. But so you have this auto-diff, which is basically auto-differentiating through your code, and you don't even have to actually understand what a derivative is to do this. And so why? And you seem to be advocating that we should actually build differentiable procedures one at a time. Is there no hope to actually think that in 3 years from now they will have smooth and auto-diff, and they will just smooth everything that we get and just auto-diff through it? I mean, like.
Yeah. So I think there's okay. Maybe one quick way of answering this is. So a few years ago, machine learning was all about gradients, and auto-diff killed this somewhat. If you were good at computing gradients, you're useless. My impression is that right now, what you can be useful for is computing those Jacobian vector products or vector Jacobian products, because essentially this is like the second order somewhat, of auto-diff. This is something that auto-diff or unrolling is not very good at. So typically, when you will run, this iterative process that will output a solution, if you run auto-diff naively, in theory, you would need to store all of the iterates. This can be very costly in terms of memory. So there are lots of different approaches to kind of mitigate this storage or computational problem. So there's lots of truncated backpropagation or implicit differentiation, the way I presented it here today, and they're actually quite linked. And so it is a bit, next front, and it's not solved, trivially by auto-diff. That being said, what you said is true. I anticipate that within 3 or 4 years, all of those sensitivity analysis of argmins, for instance, will be more or less solved. What will still remain, though, is what kind of smooth or I would say differentiable interpolation you advocate for a given problem. Here, for instance, the optimal transport problem, clearly you have a linear program that outputs a solution. Synchron, or entropic regularization deviates a bit from that to give you more smoothness, more differentiability, and something easier to compute. It's not always the case. I don't think there's a one-size-fits-all answer for all optimization problems to have automatically both something that is automatically and differentiable, automatically differentiable. You still need, I think, to work a bit on what kind of differentiability you want to get out of this optimization problem. Maybe I'm clear.
Yeah, you are. Yeah, thank you.
Okay.
Yes, Nicholas.
Marco, could you show again this formula for the Jacobian that you had at the end? Yeah. So, I mean, I suppose that you have to input alpha star, beta star. So this is like the optimal, like dual variables. But now, in practice, you will have to evaluate it at the, along the synchrone iterations. So I'm just wondering if it matters and how much it matters that when you compute that horrible formula, that you're not evaluating it at the actual alpha star, beta star.
Yeah. So this is a very good question. So this is the very classic trade-off, that you have when you have this, you want to differentiate through an iterative algorithm. It's either use autodiff, differentiating exactly 100 iterations, or you run this to convergence. Hopefully. And then, as you said, this is only valid if really alpha star and beta star. Basically, this is only valid if this thing here is 0, right? This h here is 0 because this is the reason why you can use the implicit function theorem. You have a 0 on the right hand side, and so I'm not. I think there are some works, to tell you the truth. I'm not familiar enough with them in the literature that tries to estimate how much noise you would get in the application of that Jacobian using this formula if alpha star and beta star are not exactly optimal. I guess this would typically depend, on the eigenvalues of the Jacobian matrix at the optimum, and so I haven't gone deep into the literature. If I can just provide you a hands-on perspective on this. Typically, what you would do is set a threshold. With Synchron, it's a fairly simple problem, right? It's a convex problem, so you will run you can dictate if you want the threshold of convergence. So typically, you would use a small threshold for convergence here to make sure that the implicit function theorem works. And then what we do is we compare this with backprop, and this seems to agree in most cases. One of the sources of problems, though, it seems to me, is not so much from the alpha star beta star, because this is controllable, but it's more of the inverse of the linear system. So the linear system can be ill-conditioned, and so then you start adding some regularizations and things like that.
Thank you.
So I also have a question, Marco. Can you say something about advantages of using other types of entropies other than the Shannon entropy? I don't know, the quadratic or the Tsallis. And also,
so
in particular, in this implicit differentiation, do you really use the exponential shape of the solution, or it would work in principle for every regularization?
Yeah, so this is a very good question. So for a while, I guess my position on this is because I was relying more on backprop, on unrolling. I was favoring somewhat entropy because I thought the algorithm, Synchron algorithm to get you to the solution was extremely stable and very, very effective. And so I was using the classic Synchron and then unrolling iterations of the classic Synchron. But as you just mentioned, if you start using a different regularization, in the end, the only thing that you really need to take into account is first order conditions of your problem. If the first order conditions of your problem can be, this is just a Jacobian here of H with respect to the black square. If this is a linear system that you can solve, then in theory, any regularizer should work. So this includes, for instance, let's say quadratic, which is known to provide a sparse approximation, or Tsallis entropic. I still believe that it's going to be difficult to beat Synchron when you're going to run the forward pass. So we're going to reach to alpha star, beta star. But you can now at least start using, without thinking too much about unrolling, you can start using momentum-based approaches, or recently I've been playing with momentum, and also what is the other thing that I played a bit with Anderson acceleration, which didn't work for me at all. Sorry, I forgot the other one. Anyway, so but I agree with you that switching to a implicit function theorem by opposition to unrolling gives you more freedom.
But do you see any context where use another entropy could win the Shannon one?
Yeah. So I think still, the factorization of the coupling is always going to be very useful. I have the feeling that in practice, this gives you a lot of opportunities for speed up. You're probably familiar with many works, that use factorizations of the kernel or of the couplings. So I still believe, in that sense, entropy is actually quite good. But recently, for instance, we've been playing a bit, and this follows a bit is a follow-up work on some work by Philippe as well on low rank couplings. And indeed, in that case, what you could also think is just differentiating them without so much caring for entropy. So yeah, I think the question is open. Okay. More open for me at least. It's more open now than it was maybe 3 years ago.
Thank you, Marco. So I guess it's time to leave you relax. No, thank you very much for the talk.
Thank you.
So we resume at 4.
And good luck to Jan.
Yeah, it's a bit late for Jan, right?
Yes.
Right. So I don't know if we can really do that to him.
I think it's a bit too late to tell him now because I'm pretty sure he.
Yeah, I think maybe we could take like a 10-minute break and then come back in 10 minutes.
Yes. So Jan is already online, right, Jan?
Yeah, I'm here. I'm still awake.
Okay, very long to hear.
One more hour.
So let's do 10 minutes and we come back. Is it fine?